Howdy, Dr. Sayonara.
Enter.
How was your winter break?
It was
It
nice.
Okay.
Can't actually complain too much. Why aren't my AirPods on? How was yours?
Well, it was certainly restful.
You bored?
No, like kind of tinge of guilt as to how restful it was. I think I'd like to have gotten more done.
I see. Yeah, well, we're all in that boat. I had planned to have a whole month's worth of video lectures at least recorded for intro astronomy, but yeah, that didn't happen.
Mm-hmm.
I have the first week done though.
Mm-hmm. Okay.
Hey Morgan. Hey Tyler.
Hello. Hey.
Welcome Gabe and Alex. I'm only marginally confident in my abilities to handle the technology for today's class. It could be an adventure. I apologize in advance.
It's going to be interesting going back to Kappa. I haven't had to do Kappa anything for like 3 semesters, 2 or 3 semesters.
Wow, you missed it, didn't you?
Yeah. Being told when my answer is wrong. Knowing I got something wrong. Yeah.
That's nice, isn't it?
Yeah.
Kappa's got some advantages.
There's some advantages over only having to submit like a picture of my work and then not
finding out how it's going to go. Welcome, Dan and Visma.
How's it going?
I'm well. How's your break?
Pretty good, pretty good. Got Rona'd recently, but we're doing all right.
You got what?
Corona'd recently, unfortunately.
Corona'd. Oh, yikes.
They got me. Sorry. But I'm doing all right, so it's.
How you feeling?
Could be worse. I'm feeling fine, honestly. I had no idea until I took the little test.
Did it hit your family too?
I have to assume. None of us had any symptoms, so who knows?
Odd. Yeah, my wife tested positive for the antibodies when she got blood work like in September or August, and none of us, maybe some mild symptoms all the way back in last March, but
yeah, you never even knew you had it.
But nobody else in the family tested positive for antibodies even, so we're at a loss.
Huh.
Hey, Sarah, Dante, and Liam, how's it going?
Good. How are you?
I'm doing well. Thanks for asking.
Good to hear.
Excellent. Where are we at? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think we're waiting for 3 more. So we'll give them another couple seconds to find us. There's Kylie. All right, well, we should get going. Welcome. I'm pretty excited about this class. The last time I taught this class 2 years ago, Kylie, there were 32 enrolled. So I'm actually pretty happy that it's at 14. We're at 14, and that is the most that we can have because it's the most that's allowed in ISC 229 when we get back. So obviously this week will be remote, but starting in next Monday, we'll be face-to-face. We'll be, obviously masked and sitting in the appropriate seats in ISC 229. but it would be nice to have most of you face-to-face, or all of you face-to-face. So I'm looking forward to some piece of normalcy in what will be a very weird semester. So let's go over some logistics. I will share with you. I apologize to people who are before for my only basic understanding of the technology that I'm gonna need for this particular class. So we'll see if this works. Okay, here's Chrome. I've got my Canvas page open I've got the 3 links in here, of course, for this week's Zooms. You can use those. Hopefully you've got a chance to look at what I've posted so far. There's a Kappa up. We'll be using Kappa this semester. I think I have everybody in my roster. So if you don't have a Kappa for yourself, let me know. First one we do next Thursday. I expect by the end of this week, we'll be through pretty much everything you'll need to know for that one. So some of you can already, I haven't actually checked to see if anybody's tried it yet, but I'm sure you've already gotten a head start, some of you. Let's go through the syllabus real quick. Here we are. I've got office hours. Oh, this actually changed. I'm doing this Wednesday morning instead, but honestly, I'll be here Wednesday afternoon. So if you want to stop by Wednesday afternoon, that's not a huge deal. Office hours for 300 level classes are what they are. If I'm here, the door's open, you're welcome to walk in. The worst I'll say is come back in 5 minutes or something. So this is actually wrong. I don't have office hours Wednesday afternoon, but I'll be in here. So if you want to stop by, feel free. But I do have office hours Thursday morning. Oh, actually, this is during class. I thought this was Thursday morning, Thursday afternoon. This is actually during class, so never mind. I must not have changed just from the last time. Anyway, I actually do have one office hours Thursday morning at the same time as these. Right. This was my, well, it doesn't matter. We will be meeting in ISC 229 once the semester gets back on campus. We do have a textbook, an introduction to modern astrophysics. This is, I don't want to say the Bible of undergraduate astronomy text, but it's kind of the Bible of undergraduate astronomy texts. It is a hefty tome, 1,200 plus pages. It looks pretty nice and substantial on your bookcase. And everything is in here. It is one of those really nice references to have on your shelf in case you need to know what the equation of state of a white dwarf is. It's all in here. So obviously, I sent one of the announcements early in the semester was that this is available. I have the Pearson version. The Pearson version was literally new was going for $275. I think it's crazy. Cambridge, I guess, bought the title in the past couple of years and is now selling it for $80 new. I'm sure you can find, this has been around for decades. I'm sure you can find much cheaper sources, and that's fine. Yes, I see your hand up, Hunter. Your volume is off. I can't hear you.
So then the only difference between the Pearson and the Cambridge version should be the cover?
That's an interesting question. Let me see yours. Honestly, I don't have a copy of that one. So
okay, it's second edition. I looked at yours.
I'm guessing it's identical, and I did the Amazon look inside, and those pages looked identical. I cannot verify that they're exactly the same book word for word, but it's going to be close enough that you'll be fine.
Okay.
I should ask Cambridge for a desk copy, though. That would be helpful. And maybe you can bring it sometime and we can sit down and see if the page numbers are actually the same.
Yeah.
Actually, let's do a quick experiment. Open to page 681.
681.
Is there a light curve of
yeah, figures 18.17 and 18.18?
Yeah, V 1500 sig, a fast nova?
Yes.
That's it. All right, I think you're good.
Sweet.
Cool. Excellent. We'll have 2 exams in this class and a final, 2 midterms and a final. These are the dates. If we do them in class, I did not ask, I don't know if you know some of the drama that's been going on with us in the dean's office about exams in the evening. They got mad at us a couple of semesters ago for giving exams in the evening, and I guess some student complained that they couldn't go to another class because they had to do their exams, which is ridiculous. Anyway, we have a choice of doing them in class, which would be 50 minutes, or in the evening, which would be 2 hours. And I wouldn't really change the format of the exam much, but it would be much longer format in that case. I don't have official permission to do this, so it would have to be a unanimous vote. And if there's any objections, I'm totally fine with having it in class. So let's not decide that today, but maybe sometime later this week, I'll send out a survey and ask your opinion on what you think about night exams. If they were evening exams, it would probably be, we'd probably skip class on this Wednesday and have it that evening or Thursday evening or sometime during this week in the evening instead. So stay tuned for that. We do have a final exam Monday, May 17th, which I think is the second day of exams. It goes Friday through Thursday from noon to 2:30. So pretty typical for upper level physics classes. We'll be doing weekly homeworks and projects, not weekly projects, but there'll be a semester project at the end. There'll be 3 exams at 20% each, and we'll talk about astrobytes participation. So Astrobytes is a pretty cool online site. Let me just show you it real quickly. Astrobytes.org. Oh, I forgot the O. So this is a pretty cool resource for undergrads who are interested in astrophysics and astronomy. It started out as a PhD sort of journal club thing, and that's still what the crux of it is. It's an Astro PH. So it's a Reader's Digest, really. Graduate students, present graduate students, read papers and provide summaries that are written at the level of undergraduates. And so, for instance, here's one, the galaxy main sequence, what's in the scatter. So they've taken an official paper that was written by these people in the monthly notices of the Royal Astronomical Society, which is closed access, right? So if you don't have access to the monthly notices, you can't actually see this article. However, almost every single article that's published in astronomy these days is also published on the free archive page. And that's what's linked here. Let me open this and show you. This is not the journal version, but it's a nice formatted version that's uploaded by the authors themselves that has exactly the same figures and exactly the same text as the authors themselves. So the stellar mass relation. So you can go and see the physical article with associated plots and text that this grad student is reviewing. This is a 20-page article. But this is a 1-page summary that, maybe more than 1-page summary, about what the article is about, showing some of the plots, explaining them, and explaining some of the science behind it, some of the background that you need to know to understand this article. So it's a pretty cool thing for dipping your toes into the research article space without, these articles are notoriously difficult to read. The abstract itself is, it just uses a lot of jargon and stuff you wouldn't understand unless you're in the field. So this is a nice sort of Reader's Digest version. There are other things on this site as well. For instance, so there's daily paper summaries, and I think these actually come out every day. And every one of them there's an about the author who are actual PhD students right now at various institutions around the world. So that's also kind of fun to see who else is out there doing these things. There's also these Beyond Astro PH. So if you're interested in how to go about becoming an astronomer or getting some job in astrophysics, there's actually links to articles that they've posted. And, this is, hey, if you're going to the AAS meeting, meet the keynote speaker, right? And so Astrobytes actually sits down with a lot of these keynote speakers and asks them how they got into astronomy and what they have in advice for up-and-coming scientists. The site, I think, is difficult to navigate in that in each of these, you're seeing like 5 or 6 articles. And if you want to go to older entries, you have to click the older and you see 5 or 6 more of them. And this is all since October 2020. So, if you want something from 5 years ago, it's not clear what the best way to go about finding that. And there's some really good stuff on here. So I think that's my only complaint right now about how this works. But personal experiences, current events, teaching with astrobites, and there's even guides to graduate school, guides to citizen science, guide to the major telescope, guide to astrophysical software. Interested in what to use for software? Well, they'll break it down of all the sort of various choices out there, what astronomers use, why they use them, some links to get them, things like that. So it's not just an Astro Reader's Digest, it's a comprehensive guide to being an undergrad, thinking about a career in astrophysics, if you're interested. So it's a useful site. Even if you're not interested in being an astronomer, which is fine, there are these daily paper summaries, which is what we're going to be using it for this semester. So every week, at least once, basically every week, one of us will be leading a discussion of one of these articles. So when it's your week, you will go on the archive, you'll find an article in the last month or so that looks interesting to you, and you will send us a link to the rest of us. You will put together a short-ish 5-minute or so presentation on the article. All of us will be expected to have read the astrobites anyway, before we come to class that day, so that we can have more than just a presentation. That can be more of a discussion. You're encouraged to look at the actual paper. You don't have to necessarily read it in its entirety, but if you're presenting on that particular one, maybe doing a little more digging than just reading the astrobites article and preparing a short presentation. So that is what this 5% is, both your participation in the conversations and your actual presentation of an astrobite article. So this is about a 10-minute presentation. When I had 32 in the class, obviously it was a shared thing. There was every astrobite article was taken by 2 people. With only 14 of us, we can all have our own, and we can all get a week, and it's going to be great. I'm volunteering to take the first week. I will be presenting an astrobite article this Friday. I will send you a link by Wednesday of what that article is, and if you're not presenting that week, your job before Friday's class really is to just come having read the article. So that's your homework for Fridays, in addition to doing the homework, which is due Thursday night. So there you go. It's a Thursday loaded astronomy schedule this year. Questions about astrobites?
Do we have to send everyone the article? Is there do we have to all send it by Wednesday, like every week?
Yeah. So I'll be so the timeline will basically be I'll be probably reminding the people who are due for that the last Friday, right? We'll do an astrobites article. I'll say, oh, who's next week, and then by Monday or early to mid the next week, you should have certainly chosen your article and sent me a link so that I can announce it on the page. That makes sense?
Yeah.
Okay, there is I put together a schedule, randomly assigning people. I actually used used Excel to make a random column and actually sorted it by that. So this is if you click on the astrobites presentation, submit your PowerPoint glutes. I mean, yeah, I guess this is important. I'll probably, so if you have a presentation, you'll send me the PowerPoint or the Google slideshow or whatever, and then I'll use my laptop to present it. So there is a Dropbox here for that. There's a schedule, which is linked here. And I'm not on here, but I'll be this Friday, and then starting next week, it's Dan O doing the initial student one, and then from there, just one a week. Now there's only 13 Fridays after that first one, but Connor, the last week is a Monday, Tuesday, Wednesday, but that's a Tuesday, Wednesday, Thursday class schedule, so which is weird. So our last class is actually Tuesday, May 11th, and Connor, that'll be your day. So honestly, I don't really care about this schedule. If you want to swap with someone, I'm fine with that, but you're going to need to arrange with that other person if you want that swap to work, and I'll leave it to you. Just let me know ahead of time if that happens. Cool. All right, back to the syllabus. Yeah, hopefully you'll learn some stuff this semester. And this is a rough outline of what we're going to be doing and when we're going to be doing it. The chapters in oh, I forgot. I almost called it by its nickname, and I haven't even told you what the nickname. This book has a nickname. It's a great nickname. This book is nicknamed Bob, and Bob stands for the Big Orange Book, which is very appropriate. So if I ever say Bob, I'm referring to your textbook. This is the Bob chapter on which we'll be covering, a pretty substantial portion of it. Obviously, there's a whole section on planets, there's a whole section on extragalactic, which we won't be getting to, but we'll be covering a meaty portion of the stellar, certainly the stellar part of that book. So we'll miss one class on March 22nd for Rejuvenation Day. And then our last class of the semester is actually a Tuesday, May 10th. So actually it may be May 11th, that's right. Okay, great. Questions on the syllabus? All right, and everybody's used Kappa before, so I don't think I have to go over there. If you have questions, you can let me know, but I think it should be pretty self-explanatory and straightforward. So let's get to it. Stellar astrophysics, here we go. I'm gonna stop this share. This is where it gets dicey on my technology. Seeing this? Seeing a picture of Bob on the cover? Excellent. This is the old version of Bob. Excellent. So this is Dr. Iyer taught me how to use my iPad. This is now I'm now sharing my iPad through Zoom's share. It's kind of crazy. All right, let's see if this is gonna work. Okay, so we've done this. We are. I'm going to check my notes to see if I forgot anything. I don't think so. Okay, so quick question. I know that there are some of you who have not had any astronomy class at all. Like if I say magnitude, you don't know what I'm talking about. So it's not all of you though. Quick, just raise your hand if you don't know what a magnitude is in astronomy.
I do not. How do I raise hands? And I don't know how to raise hands in this.
Well, there is a raise hand button, I think, on the toolbar. But I mean, as long as your video's on, you can actually physically just raise your hand, and I can sort of see it. Oh, Connor, you're not on though. I see. Okay,
like
cool. So
Y.
oh, there you go. I gotcha. Okay, so it was a few of you, not many. That's fine. There's no obviously, some of you have way more experience with astronomy than others in this class, and that's okay. But part of the goals of the course is to introduce you to the nomenclature and language of astronomy. It is actually different than physics. It grew up sort of parallel to physics, and it sort of merged with physics now that we understand how stars work. But it spent its formative years being a separate branch from physics altogether. And as such, there's weirdness associated with it, especially if you're coming at it from a physics perspective. So part of the learning the language of astronomy is one of the goals of this course. Okay, so we're going to start with chapter 3. This is my whiteboard now also, which is the continuous spectrum of light. We're going to skip a lot of the intro stuff. The first chapters are some foundational physics stuff, right? So chapter 1 is the celestial sphere, which is important, but we're not going to be doing any observational stuff, so that's not all that important. 2 is celestial mechanics, and 3 is light. And so this is going to be important because, I mean, you know what light is. You've had, you all took Analyte 3 with me. we talked about what light is, but it's different in astronomy, and we have ways of dealing with it that are slightly different than general physics. And it's of fundamental importance to astronomy. Why is it of fundamental importance to astronomy understanding light? Go ahead, jump in, anyone.
Because light's how we get all our information about, distant objects.
Every single, with very few exceptions, that's right. Every single thing that we know about distant objects outside of our solar system, outside of our Earth, comes from the light that we get from that. And there are very few exceptions. And so, we brought some moon rocks back. We've now brought some asteroids back. That's an exception. We get some other particles besides light, like neutrinos and cosmic rays, but by far and gravity waves now as well. It's another cool exception. But almost everything that we know about the universe comes from the light that we get from it. So that's really important. Okay, so this should all be review, not all of it, but certainly the first part of this is going to be review, but that's okay. Let's start at something we know and work on towards something that may be a little bit different. So let's specifically start with section 3.3. We're going to skip around a bit in chapter 3, but this 3.3 is the wave nature of light. So this should be a review from Analyte 2 and Analyte 3. So as you know, light is a transverse electromagnetic wave. And so what do we mean by that? Electromagnetic means there are oscillating electric fields and magnetic fields. And what does the transverse part of this mean?
The electric, or rather, they're both electric and magnetic field portions are perpendicular to the direction of travel and each other.
That's exactly right. The fields are perpendicular to each other and to the direction of motion. I thought my handwriting would be better on this tablet, but I'm not sure that it is. I apologize for that. I'm not sure it's any worse, but it's not better. Okay, so this is what that looks like. Yeah, so I'm recording this. I could not find a good way to both show my slides and a whiteboard, so I'm going to be moving back and forth between them. If you need more help, I'm going to be posting this whole video, especially this week anyway. So if you miss something, I'm happy to go back, but you're also welcome to watch it later on. So this is what that looks like. You've got oh, I can do this. Look at this. I got laser pointer too. You've got an electric field propagating in one direction and a magnetic field propagating in the opposite, in the perpendicular direction, and the direction of propagation is along the third axis. And the velocity, of course, is c. Okay, cool. All right, so obviously we can make a crude plot of the electric field or the magnetic field as a function of time, and at a particular position. Oh no, this is not as a function of time. This is as a function of space, x, and we can watch these. We can watch these fields oscillate back up and down. That's not a very good sine wave, but it's supposed to be a sine wave. And we can define some properties of this wave, right? We can define this distance from one crest to the other to be the wavelength. Define lambda to be the wavelength. And this is, of course, peak to peak or trough to trough. And we would, I'll usually put units here so that we know what we're talking about. Obviously, we're often talking about nanometers, but astronomers actually have a different unit usually for wavelength, and that is, in fact, angstroms. So again, one of the weird things about astronomy is we use different units than physicists. You'll more often hear astronomers using angstroms than nanometers, and astronomers actually typically use CGS units. In fact, the biggest complaint I've gotten for people going off to astronomy grad school is that they have to learn CGS units. Why would astronomers use CGS units? I have no idea. It doesn't make any sense, but here we are. I'm going to be saying that a lot. So obviously, wavelength's important. Frequency is important. We use the Greek letter nu for frequency in astronomy. I think you probably used F before. And that is, if you're at a single point, how many of those oscillations pass through per second. So this is hertz or 1/second. Obviously, you know this formula too. The wave speed is equal to lambda, the wavelength, times the frequency, and that is equal to c. And that, of course, is the speed of light. Oh, I need two e's there. So if you specify either the wavelength or the frequency, you get the other for free because the speed of light is a constant. We're not going to be worrying about, in astronomy, we never have to worry really about indices of refraction. We're always propagating through a vacuum. So this really is c, and these really are lambda and nu. So you c is constant. You specify either the wavelength or the frequency, and you get the other one. There's really only one degree of freedom you have in making a photon, and that is the wavelength or the frequency. Once you specify one, you specify the other. Most astronomers think in wavelength. Frequency is the more fundamental value because it doesn't change when you're changing medium, where wavelength does. But most astronomers think in terms of wavelengths. And in angstroms and in CGS units, so that's weird. Okay, as you know, light is also a particle. It comes in discrete packets called photons. And you can determine the energy of a photon. The energy of a photon is E equals hc, that's h over lambda, where h is Planck's constant. Not Planck, Planck's constant. So the shorter the wavelength, the higher the energy. Great. So this leads to the entire electromagnetic spectrum, right? There is no limit on what this wavelength can be. It can be anything. So that leads to this particular, it's a slide I show in my intro astronomy class that shows the entire electromagnetic spectrum. I'm not sure how well you can see this on my screen, but there is no real limit. The limit on the short end of the electromagnetic spectrum is these gamma rays, and that's really just limited by how energetic you can get your atoms or whatever's creating this light moving. So you're only limited by that. The faster they move, and the shorter the wavelength will be, and the higher the energy the photon will be. And on the long end, you're only limited by how big a physical thing, or how big can an object that's smaller than, yeah, I think that's true actually. I was gonna say, can an object that's smaller than the wavelength of light it's emitting emit that wave? I think that it can, but you get such low energy out here that things become eventually, well, impossible to detect. Even if those wavelengths are out there, you do need something that's about the size of the wavelength or bigger to detect the thing. So once you get, to Earth-sized or solar system-sized waves, they become impossible to detect by anything that we would have. But that leaves an awful lot of range here, right, between the very longest and the very shortest. So we have not arbitrarily, we have by historical precedent for how these things were discovered and observed, split the spectrum up into these 1, 2, 3, 4, 5, 6 categories. Gamma rays being the shortest, then X-rays and ultraviolet. Visible being the very small range here, which our eyes are actually sensitive to, as well as infrared and then radio. Microwave you'll sometimes see as sort of the bridge between infrared and radio, but that's not a formal designation, I would say. None of this is really all that formal. This is also cool for the intro astronomers because it shows you, what other things have the same size as the wavelength of that particular wavelength. So again, by the time you get down to high X-rays, you're down to atom-sized things, right? Here's the frequency scale on the same range in hertz. Here's the energy in EV, and some things on Earth that give off those, and some things in the universe that give off those particular wavelengths. Anyway, this isn't anything new to you. I do want to, let's add another page here. Just have this, so the EM spectrum, oops. Electromagnetic spectrum. I'm going to write these down so you have them in your notes, not because they are, there are no real hard boundaries, right? Where does gamma ray end and X-ray begin? People will disagree on this. I'm going to write down some numbers in the book, just so you have them in your notes and you can sort of think about these scales. So region and wavelength. So gamma rays are any wavelengths less than 1 nanometer. X-rays between 1 nanometer and about 10 nanometers. Ultraviolet will go from about 10 nanometers to about 400 nanometers. And this is the one where, the only one where there's really a hard boundary. And that is visible, because this is defined by what we can actually see. It's slightly different from person to person, but for the most part, our eyes are sensitive to photons going from 400 to 700 nanometers, which is a very small range, right? All these others are at least factors of 10 or more. This is not even a factor of 2 in wavelength for the visible part of the spectrum. Infrared. By the way, I'm not looking at the clock, so if I start to go along, somebody ping me or shout me. Or looks like I'm good. I got 15 minutes left. 700 nanometers, obviously, to about 1 millimeter. And finally, I'll put microwave down here, because I think the book does 1 millimeter. But again, you'll see different sources and different people give slightly different boundaries to these. 1 millimeter to say 10 centimeters, and finally radio. And some people will leave microwave altogether. Anything greater than 10 centimeters. Okay, now our eyes are pretty good at not only detecting light that's between 400 and 700 nanometers, our eyes are really good at detecting the differences between the wavelengths between 400 and 700 nanometers. And we, in fact, interpret those different wavelengths as different colors. And so you can define different regions of the visible part of the spectrum based on what our eyes actually see for that particular wavelength. And so let's just, here is the, again, the cartoon version. We start with red at the long end and then go to indigo and violet at the blue end. These really just become more purpley as you go up. But let me just write some of these down. For the visible, Purple happens at about 445 nanometers. Blue at about 475. These are all nanometers. I'm gonna stop writing them down. Green at 510. Yellow at 570. Orange at 590. And red at about 650. And again, these are ranges. It's sort of the middle of the blue, the middle of the green, the middle of the yellow, the middle of the orange. These are very small differences in wavelength, right? It's kind of amazing that our eyes can tell immediately and without question the difference between a 510 and a 570 nanometer photon. Our eyes have developed the ability to do that quite well and quite easily. So again, memorizing these numbers is not something I want you to do. What do I want you to do? I want you to know that the blue is the short end of the spectrum and red is the long end of the spectrum. I want you to know that that the blue is the high energy end of the spectrum and the red is the low energy end of the spectrum. Those are the important things to sort of take away from this particular thing. Okay, great. So those are the basics of light. We'll get more into light and how we actually measure the brightnesses of things, which is this whole other crazy thing that we do in astronomy. But let's start this whole topic with just stepping back for a minute and thinking about what it is that we're going to be studying in this class. This is a class on stellar astrophysics. We're going to be, this entire semester, the goal will be to understand the structure and evolution of these things. It turns out they're fairly simple things. You can write down, in fact, 4 differential equations, which pretty well characterize the structure of a star. Now, those equations get kind of complicated, and the details associated with that do get very complicated, and it can take rather large computer codes to get the details right. But the basics are pretty simple, and that's what we should get to even by this time next month. We should have a pretty good understanding of how stars are structured and why they're structured that way. And we could even solve some of those basic equations to give yourself some, what's the temperature profile of the sun look like? What's the density profile of the sun look like? Those are things that we can answer, in the first month of a stellar astrophysics course. So that's our goal. First, we need to think about some observational properties of these things, though. So here is a nice picture of some stars. Obviously, when I teach this in intro astronomy, I ask the students, tell me all the things you can know about these stars just by looking at them, right? I'm not going to go through that exercise here, but it's basically just brightness and color and relative position. That's really all you get from this. And the things we want to know and can know about stars, both from the brightness and from spectroscopic data, is almost limitless. We get all kinds of information. So let's go through and talk about quickly some fundamental parameters of stars, some measurable things that we can measure about stars. Let's go ahead and I'll throw it open. I've got a list of 2, 4, 6 things here. Go ahead, see if you can get them. Jump in.
I'll start with the obvious one, brightness.
Brightness. Okay, that is sure. Brightness is our perception of that, though, right? How bright a star appears. But fundamental brightness, luminosity, is certainly on the list. That is how much energy is the star giving off per second. That is a fundamental property of that star. Its brightness is actually not a fundamental property because it depends on how far away it is. So, fundamental properties of stars, number 2.
Surface temperature?
Temperature, absolutely. obviously, well, I don't know if it's obvious, the sun, stars do not have a constant temperature all the way to the center. It gets hotter as you go in. But surface temperature is a fundamental property that is measurable. And so we like that one. Yep. What else?
Distance?
Distance. Yeah. Again, this is sort of on here. I'm going to asterisk. It's not a really fundamental property of that star. The distance obviously changes as you move it around, but it doesn't physically change the makeup of the star. But it's going to be really important and really, in order for us to get some of these things that are fundamental properties of that star, we're going to need to know that distance. And so it becomes fundamental to understanding stars, even if it isn't fundamental to the star itself. Okay, I got three more here. Mass.
Mass.
Yes. Thank you, Dante. How massive it is, how much stuff it has in it. Yep, definitely. Two more.
Diameter.
Diameter. I'll say radius, but same thing, the size of the star. Yep. I got one more on my list.
Composition.
Composition is important. Yes, I'm going to say
Might kind of be part of mass, I suppose.
you can have this two stars of the same mass that have very different compositions. I'm going to put this. I actually have two other categories below that I have in less important, and that is there not because it's not important, but because if stars vary dramatically in their composition, they would look very, very different. But only because stars don't vary all that much in their composition, at least normal stars. And so this becomes sort of a secondary component. It does affect the structure of a star, and changing the composition will. We'll talk about why as we go along. But it is a secondary effect to some of these others for how the star actually looks to us. Good. So there's actually one more in the less important and one more in the fundamental, I would say.
Is it velocity?
Velocity, I don't have on this list. That it's certainly something we can measure, and it's important for understanding perhaps where it came from or its origins. But how it's moving relative to us depends on how both we're moving and the star is moving. So again, it is not a fundamental property of that star, but more a property of the difference between us and that star, and doesn't really impact its structure. So I'm not gonna put that one down, but good guess.
Would color be one?
Color is very much related to temperature. So I'm gonna, it's sort of on here already. We'll get to that in a bit. But we've already got that one pretty much.
Is density, or is that with mass and radius?
Yeah, Matt, with mass and radius, you've got density too. That's a good guess though. Yep. Liam, go ahead. What's that? Age. That is the last one on my fundamental list. Good job, Liam. You get the star for the day. Age. Obviously, it's stellar structure and also stellar evolution. The age is going to be important. How are these parameters changing over time? Why are they changing over time? And how do stars behave as they go? Anyone take a stab at the less important one? I'll give it to you if nobody wants to take a stab at it. Obviously, there's a million less important ones. Which one have I happened to write down? I'll tell you, it's spin rate. So that actually can affect it's a fundamental property of that star, what its angular momentum is, and the faster it's spinning, stars that are spinning fast do have fundamental differences in their structure to stars that are spinning slowly. So that becomes important. Okay, so we're going to drill down on all of these and how can we measure each of these, right? Again, we're only receiving star light from these things. We can't obviously physically measure the distance almost ever, although that's changing rapidly. There's no meter stick that we have that goes that far. We have fundamental ways to measure mass. We have fundamental ways to measure temperature. Radius is a bit more difficult because, well, we'll get into it. There's ways that we can determine all of these parameters for stars. And the first part of this class is understanding the observational origins of understanding what we know about stars. So we're actually going to start with distance because it is extremely important. In fact, if you don't know the distances to things, almost none of these other things are possible to measure. So distance is going to be our first go. So how do we measure distances in astronomy?
Parallax.
Parallax, that's right. It was as a pause. I'm glad you jumped in. I wasn't waiting for a jump in, but I'm glad you did. What is parallax? I've got 3 minutes, so let's do a quick parallax demo. I do this in my astronomy class, and I think it's a good exercise. Find a thing that's not on your computer screen, but is further away from that, and hold your thumb out in front of your face and cover that thing up with your thumb and close one eye, right? So if you've covered it up, if you open the other eye now, you'll notice that your thumb has moved. It's no longer in the same spot. And if you move your thumb closer to yourself, your nose, your eyes, you'll notice that you can do the same thing, but that it's moved a different amount. That is parallax, right? Our vantage, if you have two different vantage points from of an object, how it appears to move against background objects tells you how far away that thing is. This is why we have eyes on both sides of our head. This is why we have depth perception, that we can judge distances based on our vantage points on the opposite side of the head. Obviously, that baseline is not big enough to measure distances to stars. Our baseline of our eyes doesn't work much beyond 10 meters or so. But we do have a moving platform in astronomy that we can use to measure distances to much more distant things. And that is, of course, the Earth's orbit around the Earth. If we see, this is the basics of how this works. We'll talk about the details next time. But if we see a nearby star from, let's say, in January against this particular star, let's say these are really far away, and then in July, 6 months later, we see it against a different, how far this thing seems to have moved in angle space is related to how far away that object is. Just like your thumb, the closer that star is to us, the greater it will seem to move with respect to the background stars. Okay, I will go over the geometry of this and how we can actually measure this stuff next time, but I'm out of time today. So I'll stop there. See you Wednesday. Enjoy the rest of your Monday and Tuesday, and we'll pick it up again on Wednesday.
Thank you, Doctor.
Have a good day.
Bye.
Bye.
See you then.
Bye, Liam.
Hello.
Hey, Bisma. Okay, let me stop sharing and stop recording.